Imagine you are on the moon. Your job for the next 8 hours will be exploring, traversing up and down lunar hills, sampling rocks, and setting up equipment. Temperatures can reach a blistering 250 degrees Fahrenheit. Luckily, you have a portable life support system, a backpack that provides oxygen, water, power, and, for the excruciating temperatures, a cooling system. Under the Artemis program, NASA and its partners are planning to return astronauts to the moon, and the agency is testing new spacesuit technologies. As a new age of exploration heats up, engineers are looking to improve how to keep astronauts cool in space. Outside the International Space Station, astronauts perform extravehicular activities, EVAs, also known as spacewalks. During the Apollo era, spacewalks took place on the lunar surface, and with the Artemis program, humankind will once again return to live and work in the harsh environment of the moon. Future plans call for spacewalks to last longer and be more demanding, not just on the astronauts, but also on the spacesuits and systems that protect them and keep them alive and healthy. NASA has been working on advanced technologies needed for next-generation spacesuits. NASA's reference design, the Exploration Extravehicular Mobility Unit, or the XEMU, features greater mobility, visibility, and flexibility. This prototype is just the beginning. To meet the needs of future exploration as part of the Artemis program, NASA will share its newest designs, research, and data with commercial industry, whom NASA will partner with to build the next-generation spacesuit. It is an effort that will benefit from NASA's most recent studies and the agency's 50-plus years of spacewalk experience. Spacesuits are essentially a spacecraft made for one. They have many important life-preserving components, but none is more complex than the system to regulate the temperature of the astronaut. Engineers call this cooling system the thermal control loop.
The thermal control loop is part of the portable life support system, or the backpack that the astronaut wears when they do an EVA. The thermal control loop is designed to keep the astronauts cool. When the astronauts are doing spacewalks, they can be exposed to extreme temperature swings, say up to 250 degrees Fahrenheit. The thermal control loop is part of a system that consists of a liquid cooling ventilation garment, or LCVG, that the astronauts wear under the spacesuit. It consists of tubes that are filled with water that circulate from water pumps in the backpack to keep the astronauts cool.
During the Gemini program, engineers realized that astronauts not only needed protection from the temperatures of space, but also from the heat generated inside the suit, from their own bodies as they worked. Originally, the suit designers thought that airflow over the astronaut's body would keep temperatures regulated. What they discovered was that air cooling in a spacesuit is insufficient to do that job. During the Apollo era, it was decided running cool water through a garment that covers the body could help keep the astronauts from overheating. The means of cooling the astronaut was now an essential life-sustaining element to the spacesuit and was here to stay. The spacesuit currently in use on the space station, developed in the 1970s, also uses a water-cooled garment. Circulating water is still the best way to cool an astronaut. However, improvements can be made on how to move that water through the system, using new technologies and materials to test how to make the essential cooling system safer and more reliable than ever before. The result of this research is SERFI, the Spacesuit Evaporation Rejection Flight Experiment, all the critical elements of a spacesuit cooling system in one box. 2 SERFI units have been built, one to work here on Earth in our gravity, and another SERFI unit meant to be tested in the absence of gravity, in space. On board the International Space Station, astronauts take advantage of the microgravity environment to perform a variety of science experiments. and to test exploration technologies. When engineers developed the spacesuits for the Apollo and Space Shuttle eras, NASA did not have a space station in operation. Today, the station presents a perfect platform for engineers to use microgravity to put the SURFY cooling system to the test.
In that experiment, we will test a couple different versions of the water pump that will be used to circulate the water through the system. We'll test temperature sensors, we'll test pressure sensors, integrate all those into one little package and test them for long duration to see how they'll perform over the expected life of a spacesuit.
SURFY shows how the water will move through the system as if it were inside a spacesuit, cooling the astronaut. But a spacesuit cooling system needs to do more than just circulate water. As the astronaut works, their body generates heat, which is transferred into the liquid cooling and ventilation garment. A thermal control loop needs a way to remove the heat from the water that is circulating through the system. That's where SWIMMY comes in, the spacesuit water membrane evaporator.
SWIMMY consists of some porous hollow fiber membranes that are contained in a metal manifold. When warm water flows through the porous membranes and then is exhausted into space, the cool water continues through the porous fibers and continues to flow through the LCVG liquid ventilation garment to cool the astronaut.
With the means to run a cooling system and offload heat and gases, the SURFY unit runs for 8 hours at a time, the span of what a spacewalk might last in space or on the moon. The tests are run again and again, simulating the rigors of what a spacesuit thermal control loop might encounter during its life cycle. Astronauts take water samples from SURFY for analysis. Just as a spacesuit might sit in storage for a time between spacewalks, like during a trip to the moon or Mars, SURFY is sometimes switched off. This time of dormancy is when contaminants can grow in the system.
That's when the bugs, the microbes, grow in the water system. And those little guys grow and they reproduce and they can grow through the system. They'll clog your filters, and once your filters get clogged, the water stops flowing.
When the water stops flowing, the suit stops cooling. Contaminants in the water are such a problem for current spacesuits that astronauts set aside time for regular water maintenance chores every 90 days. The SURFY tests hope to demonstrate that new technologies and materials will be far more robust in working through water contamination issues, reducing the risk of the cooling loop failing.
We don't want to have to worry about water quality. We want to be able, we've joked among the team, we want to be able to pour chicken soup into the exploration EMU and it'll still run the way it's supposed to run. Even if there's microbes in there that the system doesn't care. So we want the filters to catch the microbes, and if the filters don't catch the microbes and they flow through the pumps don't even notice the microbes or the contamination or whatever's in the water. They keep operating the way they're supposed to operate. We want our crews to be spending their time exploring, not running maintenance procedures on our spacesuits.
All the testing for SURFY in space is duplicated on Earth, with a twin SURFY running in 1G, Earth's gravity. By testing here and simultaneously testing in the microgravity of the space station, engineers can infer how the cooling unit will run in the 1/6 gravity of the Moon, the 1/3 gravity of Mars, and all points in between. The knowledge gained from building and testing the twin SURFY units is already paying off, as work is underway building a full-size backpack for NASA's prototype exploration spacesuit.
How's it going to perform in microgravity? Well, by sending SURFY to a space station, we can actually test how it's going to perform in microgravity. That in itself buys down the risk. So now there's one less unknown that we have to worry about when we send our hardware off to do what it's supposed to do.
I am so excited that SURFY, SWIMMY is on orbit, that we're working great, our ground unit is working great. SURFY has made a difference. We've had engineers, scientists, thermal analysis, water experts. It's been an exciting multi-discipline collaboration.
It's a collaboration that will inform spacesuit technologies for the Moon and beyond. A new design for a thermal control loop and its ability to help regulate temperatures for astronauts during exploration can benefit from the data gathered from SURFY, making it one cool little experiment.